Hey everyone, and welcome to another deep dive. Today we're going to be tackling computational complexity.
Sounds fun.
Yeah, it's all about how hard it is for computers to solve certain problems.
Right.
And we're going way back in time for this one,
Okay.
all the way to 1971,
Wow.
to a paper by Stephen Cook called The Complexity of Theorem-Proving Procedures.
Okay.
This paper basically laid the foundation for figuring out just how difficult it is for computers to figure out if a logical statement is always true no matter what.
Exactly.
You know, the sky is blue or the sky is not blue.
Right.
Kind of a simple idea,
Yeah.
but for computers, it can be surprisingly tricky.
Yeah, it's true. These are called tautologies.
Tautologies.
And Cook's paper showed us that even though they seem simple, they can be computationally challenging.
Okay.
And his work introduced this idea of polynomial reducibility.
Polynomial reducibility.
Yeah, which is a way to show that seemingly different problems are actually connected in terms of how hard they are to solve.
Okay, that sounds intense. Can we break that down a little bit?
Sure. So imagine you have a magic box.
Uh,
We'll call it an oracle. And it can instantly solve a particular problem.
right.
Polynomial reducibility is like saying, hey, if I can use this oracle to quickly solve a second problem, then that second problem is no harder than the first one.
So it's like finding a shortcut
Yeah,
by using a solution to one problem to tackle another one.
exactly.
Okay.
And Cook showed that lots of other complex problems could be reduced to this tautology problem.
Wow.
It's like saying a whole bunch of locked doors could all be opened with the same key.
So if we could figure out how to determine if a statement is always true, we could unlock solutions to a bunch of other really hard problems.
Exactly.
But why is the tautology problem so difficult for computers to solve?
Well, think about it this way. To figure out if a statement is always true, you have to consider every possible combination of truth values for all the parts of the statement.
Okay.
As a statement gets more complex, the number of combinations just explodes.
Right.
It's like trying to find a specific grain of sand on the beach.
Oh, wow.
You have to look at each one individually, and that can take a long time.
That sounds tedious,
It is.
even for a computer.
Oh.
So how does Cook's work connect to what we hear about today with things like P versus NP problems?
Yeah, that's a great question. So Cook's work really laid the foundation for our understanding of P versus NP,
Okay.
which is one of the biggest unsolved mysteries in computer science.
Right.
P stands for problems that computers can solve relatively quickly.
Okay.
NP refers to problems where it's easy to verify a solution once you have it, but finding that solution in the first place can be incredibly difficult.
So P problems are like finding a word in the dictionary.
Uh-huh.
And NP problems are like trying to solve a Sudoku puzzle.
Exactly.
You can quickly check if the solution's correct, but finding that solution can take ages.
Yeah, that's a great analogy. And so Cook showed that this tautology problem is one of the hardest problems in this NP category.
Okay.
And it's what we call an NP-complete problem.
NP
If we could figure out how to solve tautologies quickly, it would mean that P equals NP, and we could efficiently solve a vast array of problems that currently just seem intractable.
Wow, so this seemingly simple idea of checking if a statement is always true has implications for some of the biggest challenges in computer science. This is why I love these deep dives. You never know where they'll lead you.
Yeah, it really highlights how interconnected these seemingly abstract concepts are to, like, real-world problems.
Okay, so I think I'm starting to grasp the significance of this tautology problem. But I have to admit, my brain is still a bit fuzzy on the whole polynomial reducibility thing.
Right.
It feels kind of abstract.
Okay.
Can we maybe try a real-world example to make it a little clearer?
Sure. Let's say you're planning a road trip,
Okay.
and you want to find the shortest route that hits all the cities on your list.
Yeah.
That's actually a famous problem in computer science called the traveling salesperson problem.
Okay.
And it turns out that this problem can be reduced to the tautology problem.
Wait, what? How can figuring out the shortest route for a road trip be related to checking if a logical statement is always true?
Yeah, it's kind of like translating the road trip problem into the language of logic.
Okay.
You can create a logical statement that's true if and only if there's a route that meets certain criteria,
Right.
like visiting all the cities and staying under a certain mileage limit.
Yeah.
Then you can use the same techniques that we use to solve tautologies to find the solution to the road trip problem.
So it's like transforming one problem into another that we already have tools to solve.
Exactly.
Oh, okay. I see.
And that's the beauty of polynomial reducibility. It gives us a way to connect these seemingly different problems and leverage existing solutions to tackle new challenges.
Mm. That analogy really helps. So I'm getting that polynomial reducibility is like a powerful tool for understanding how problems relate to each other in terms of difficulty. But it also kind of raises a question for me.
Yeah.
If we can reduce so many hard problems to the tautology problem, why don't we just focus all our efforts on cracking that one?
That's a great question, and that really gets to the heart of why the P versus NP problem is so challenging.
Right.
While we've shown that many problems can be reduced to the tautology problem, we still haven't found a way to solve the tautology problem itself efficiently.
Okay.
If we could, it would mean that P equals NP, and we'd have a shortcut to solving a huge class of problems that currently seem intractable.
Right.
But so far, nobody's been able to find that shortcut.
So it's like we found the master key, but the lock is still incredibly complicated.
Exactly. And that's the ongoing mystery of P versus NP. It's one of the most fundamental questions in computer science. And it all started with Cook's groundbreaking work on the tautology problem.
It's amazing how this one paper from the 70s has had such a huge impact on computer science, even decades later.
Absolutely. It's a testament to the power of theoretical work to shape our understanding of computation and guide the development of new technologies.
So to recap, we've learned that determining if a statement is always true, the tautology problem, can be surprisingly challenging for computers.
Right.
Cook's work on polynomial reducibility showed us that many other tough problems can be boiled down to this seemingly simple question. And this insight has profound implications for the famous P versus NP problem.
Exactly. And the ongoing search for solutions to these problems continues to drive innovation in fields like cryptography, artificial intelligence, and optimization.
You know, it's kind of humbling to think that something as seemingly basic as checking if a statement is always true can have such a big impact on the world.
Yeah.
It really makes you appreciate the power of ideas and the interconnectedness of knowledge.
I completely agree. It's a reminder that even the most abstract concepts can have profound consequences for the technologies that we use and the problems that we're able to solve.
Well, I don't know about you, but I'm feeling like I need a mental break after all that brain-bending discussion about computational complexity. How about we take a quick breather and then come back to explore some real-world examples of these NP-complete problems that are making our lives so interesting. All right, so we've explored like the theoretical side of computational complexity, this mind-blowing idea of polynomial reducibility.
Yeah.
But where does all this like brainy stuff actually show up in our daily lives?
Well, believe it or not, NP-complete problems are lurking everywhere. Remember that road trip example we talked about?
Yeah.
The traveling salesperson problem? That's a classic NP-complete problem.
Okay.
It has real-world applications in things like logistics, delivery routing, even microchip design.
So figuring out the best route for a delivery truck or designing the most efficient layout for a computer chip.
Exactly.
Those are problems that share the same fundamental complexity as our friend, the tautology problem.
Precisely. And it's not just about finding the absolute shortest route or the most compact layout.
Right.
It's about finding the optimal solution
Okay.
among a vast number of possibilities.
Right.
As the number of variables grows, more cities to visit, more components on a chip, the number of potential solutions explodes exponentially.
That makes sense. So how do people actually deal with these NP-complete problems in the real world? I mean, if even supercomputers struggle to find like the perfect solution, how do we get anything done?
That's where things get really interesting.
Okay.
While finding the absolute best solution in a reasonable amount of time might be out of reach,
Yeah.
there's a whole field of computer science dedicated to finding good enough solutions.
Okay.
What we call approximation algorithms.
Approximation
Or
algorithms.
you're using clever strategies called heuristics.
Heuristics. So instead of aiming for perfection, which might take forever, we try to find solutions that are pretty darn good
Exactly.
and that we can compute in a reasonable amount of time.
Think of it like packing a suitcase.
Okay.
You could spend hours trying to find the absolute most efficient way to pack everything perfectly, or you could use some tried and true strategies to get most things in there pretty well.
Right.
In many real-world scenarios, a good enough solution that we can find quickly is more valuable than a perfect solution that takes ages to compute.
That's a great way to put it. So even though these NP-complete problems present like a huge challenge, We found ways to work around them and find solutions that are practical for like real-world applications.
Absolutely, and the research continues.
Yeah.
Computer scientists are constantly developing new algorithms and techniques to tackle these tough problems more efficiently. And who knows, maybe one day we'll even find that elusive shortcut that proves P equals NP.
Well, I'll keep my fingers crossed for that breakthrough.
Mm.
But even if it doesn't happen, it's amazing to see how the theoretical work of people like Stephen Cook has had such a profound impact on the way we approach practical problems
Yeah.
in fields ranging from logistics to artificial intelligence.
I couldn't agree more. It's a testament to the power of curiosity and the interconnectedness of seemingly disparate fields of knowledge.
Well said. So as we wrap up this deep dive into the world of computational complexity, I hope you've come away with a newfound appreciation for the beauty and the complexity of the problems that computers are trying to solve, and the brilliant minds who are working to unravel those mysteries.
And remember, the next time you're struggling to pack a suitcase or plan a road trip, you can take comfort in knowing that you're grappling with some of the most fundamental challenges in computer science.
That's a great point. It makes those everyday struggles feel a little more epic, doesn't it? But for now, we'll leave you to ponder the mysteries of P versus NP and the surprising power of the tautology problem. Until next time, keep exploring, keep questioning, and keep diving deep.